Hello student, good morning to everyone. I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about the minus multistratin. In minus multistratin we have seen complete retrosynthetic strategy as well as the synthesis by using the suitable reagent and the proper reaction condition. We arrived or we reached to the natural product, that is a multistratin, and the reagent collectively we have used for the synthesis of multistratin are like methyl magnesium bromide in presence of ether, which is a Grignard's reagent for the introduction of methyl group. Then second one we have used, that is a chromium trioxide, which in presence of acetone, which is a Coulin's reagent used for oxidation of alcohol to the ketone. Then third one we have seen Wittig reagent used to introduce the exocyclic double bond, that olefin, that is the purpose of this. Then next one we have used hydroboration oxidation reagent B2H6 in presence of THF and sodium hydroxide in presence of H2O2. Then tosyl chloride in presence of pyridine, it is used for the protection of that alcohol. Next one we have used lithium iodide in presence of acetone, is then that tosyl group is easily depart or leave and the iodine is attached over there. And then second last, that is a 3-pentanone-enamine derivative in presence of Grignard's reagent and THF used as a solvent. And finally hydrolysis we got the minus multistratin and the isomer, the desired natural product we have obtained there. Now what we are going to discuss today, is a minus Pentanomycin. So total compound we are generally by using as a Chiron approach, there are the 6 molecules we are going to study. That 6 are the target molecule, and as we know that target molecule means what, whose synthesis been planned is known as a target molecule. Number 1 we have already seen, what is that? Yes, propanediol. Number 2 R and S epichlorohydrin. Number 3 L plus alanine. Number 4 multistratin, and number 5 is a Pentanomycin, and number 6 is a minus chemic acid. These are the natural product we are going to learn. So far we have learned 4 target molecule. Now is a 5th one today we are going to discuss, that is a minus Pentanomycin. It is one of the natural product, is very useful as a medicinal point of view is concerned. And let us see how this natural product, what are the strategies is used. Here is a retrosynthetic strategy via Chiron approach is generally adopted or used. How that is used, let us see some of the introduction regarding that minus Pentanomycin. The antibiotic Pentanomycin, it is an antibiotic and has been the subject of structural and the chemical studies including X-ray analysis. Structurally remote from a carbohydrate analysis of the molecule reveals hidden carbohydrate type symmetry, and which was uncovered and cleverly exploited by Motapan, Verheiden and co-workers. These are the scientists, they put this compound here in a beautiful manner. Analysis of the structure of Pentanomycin reveals the presence of a functionalized cyclopentanone system, and which in principle can be generated from an intramolecular aldol condensation of a ketoaldehyde precursor. That is a main principle is employed here for the synthesis of this Pentanomycin. The retrosynthetic analysis shows how such an acyclic precursor can be generated from a carbohydrate, and eventually if one ignores the branched hydroxymethyl group, the 5-carbon backbone can be related to a carbohydrate known as stereochemistry at a C2. And note that the aldehyde function needed for the eventual cyclization and the location of the ketone carbonyl function comply with the rule of, as we know that rule of 4 or 5, have hence the possibility of a chiron derived from function furanoid template, and as we know that template are the starting material. The configuration at the secondary hydroxyl group converges with C2 in 1,2,5,6 diisopropylidine alpha D glucofuranose, and using such a derivative also ensure stereopacific chain branching, and the 2 chiral center in the target can be secured early in a carbohydrate precursor. And the main challenge reside in the cyclization of an appropriate derivative to the cyclopentanone, an unprecedented transformation from carbohydrate precursor, and scheme shown that the hydroxymethyl group was easily introduced via nitromethane reaction to give the product. Transformation of the nitromethyl group to a protected hydroxyl methyl and chain shortening afforded the derivatives with the 2 asymmetric center secured, and methanolysis followed by acetonylation led to a product which could be subjected to the basic catalyzed elimination to provide the enol ether type of masked methyl ketone. An acid treatment afforded the desired ketoaldehyde precursor, and which after careful experimentation was subjected to intramolecular aldol condensation. Note condensation to give the protected Pentanomycin derivatives, and note how dehydration was done under acetylysis condition to avoid hydrogenation. And finally, this is a very important term used here. Finally, enzymatic deacetylation and avoid hydrolysis gave minus Pentanomycin identical with the authentic natural product. And whatever natural product we isolated, same we are getting here. That is authenticity of that with that natural product. The total synthesis of the Pentanomycin by this route also confirm its proposed configuration. The synthesis of 6-deoxyamino Pentanomycin followed the similar route. So now first, as we know that we generally this thing is divided into as a two part. Number first part is a retrosynthetic analysis. First let us see the retrosynthetic analysis. Retrosynthetic analysis, right? And as we know that retrosynthetic analysis means what? The process of breaking down target molecule into convenient starting material by using disconnection, and FGI is known as a retrosynthetic analysis. And as we know that this is a retrosynthesis. Retrosynthesis means what? An imaginary but logical reverse chemical reaction which help us to reach the reactant starting from the target molecule is known as a retrosynthesis. And now in the retrosynthetic analysis, two terms are involved. One is a disconnection and second one is a FGI. Disconnection means what? An analytical operation which break a bond and convert a molecule into a possible starting material is known as a disconnection. And FGI means what? Functional group interconversion. Functional group interconversion means what? Again, one of the functional group converted into another functional group so that disconnection becomes possible and is known as a FGI. Now let's as we know that is the target molecule Pentanomycin. The structure of Pentanomycin is this one. As we know that this is alpha beta unsaturated type of the compound, and here this is one of the CH2OH primary alcohol, and then there will be a 2-hydroxy group. They are below the plane. So this is our target molecule, and as we know that this is a target molecule. Target molecule means what? Whose synthesis being planned is known as a target molecule. And when if you use here alpha beta unsaturated compound, as we know that it is prepared in the aldol, intramolecular aldol condensation, so that you will get over here. So do the FGI function aldol condensation or aldol approach you can use over here. That is a dehydration. What you are going to get? So at beta position generally we are putting as this one OH hydroxy. Let us see this one, and now they are as it is OH. This one is a OH, then next one also as a OH as it. Look at, we put the beta hydroxy there because we are using as a aldol intramolecular aldol condensation approach over there, and now it is breaking like this. So what you are going to get here, you are going to get the compounds are like this. So let me write here negative charge, then this one they are as it is OH, then you can put OH, another here what is happening, C double bond O and the H, right? Here again OH as it is. Then do that FGI, or what we can call it as a synthetic equivalent for this. We can write as a synthetic equivalent for this negative. This is a synthon, and as we know that synthon means what? It is associated with the polarity, and synthetic equivalent it require, and synthetic equivalent we can write here is a methyl group, and then this one C double bond O, then here this group as it is OH dash OH as it is, and then this aldehyde group also as it is. We are writing only as a synthetic equivalent over here, or we can write synthetic equivalent by using as this and this are the same. You just bring, we just bring it as a hydrogen atom over there, right? And now we can at an equilibrium we can bring this hydrogen atom like this here, so that what you are going to get negative charge over there, so that you can this double bond for sake of convenience negative charge. If I am a negative charge, this is going to attack on a carbonyl group, and finally you are going to here you can do as a FGI again. functional group interconversion, so that you are going to get the compound like this O here, this one, then here becomes as a double bond, this is as it is, sorry, here just you write as a OH here, just joined as a OH over there, OH as it is, and then this hydrogen atom as it is, another hydroxy group which is also as it is. And after that again you can do the FGI over here, do FGI, functional group interconversion. Functional group interconversion means what? One of the functional group converted into another functional group, so that disconnection becomes possible. Therefore we are going to get over here FGI, just here, sorry, here is a OH, we are writing over here, and now what, this hydrogen atom get replaced by here, I am writing this one properly over here, here OR, then this double bond as it is, then this hydroxy group which is also as it is, then OH, and this one OH also as it is, right? And after that again do the FGI, functional group interconversion. After doing as a functional group interconversion, what you are going to get here, you are going to get this one, you can convert into this group into as a this one functional group hydroxy, then other things remains, other thing is remains as it is here OH, then you can put both the hydroxy group below the plane, and here we can write as a OH as it is, and this again you can convert, do the FGI, functional group interconversion, this you can convert into the hydroxy, that group, that is a D-glucose. Here you can CHO, then here OH, then HO over there, then 3OH on the right hand side. This is a D-glucose, as we know that, right? This is the structure of D-glucose. This D-glucose we can this you can convert at an equilibrium. You can write this into this also, there OH, then OH, hydroxy group over there, then here OH, and here is a hydroxy group. The name of this compound is a D-glucose, right? This is a again D-glucose, and this D-glucose again do the FGR, functional group interconversion. This can be obtained from this one, that is, this is a structure over there OH, then you can write OH, and here you write HO, and here also as a HO, that is a D-arabinose. The name of this D-arabinose, this is a structure, and from that we can prepare. This is a retro of this minus Pentanomycin. Now let us start how we can synthesize this in the laboratory. That is half of the part is completed over here. Now we are going to learn the synthesis of this by starting as a, now we have to go reverse and so arrive at the target molecule, or you can achieve the target molecule or the desired product here. Now do the synthesis, that is the retrosynthetic analysis over here. Now is the second part. Second part will be the synthesis now. Synthesis, right? And now in the synthesis, take the starting material. As we know that starting compound we got here is this one. This is OH, then OH, then OH. This is a starting compound we got, that is a D-arabinose, right? And this compound further treated with H plus or acetone in presence of H plus. As we know that the mechanism, and what is the purpose of this acetone in presence of H plus? It is used for the protection of 1,2-diol. Look at here, 1,2-diol, and here also as a 1,2-diol, and therefore you are going to get the product here like this. This you can write 1,2-diol, write this, and here hydroxy O, this is a protected, and this one OH only remains free to carry out the reaction. Now then oxidation reaction with the help of CrO3 in presence of acetone, that is a Coulin's reagent. What it will do? It is oxidizing reagent. This secondary alcohol get oxidized into the ketone, and you are going to get the formation of the product here, C double bond O. Other thing remains as it is. Remember here. So how they are remains as it is? They are like this, right? And now further we can use here is a nitrobenzene, as we know that. Sorry, nitromethane, NO2 in presence of base here. Base sodium hydroxide or sodium hydride you can use. What is going to happen? This base will abstract the proton. Formation of the carbon is well stabilized due to the resonance effect, because nitro group is a electron withdrawing group, and therefore it will stabilize, and that is going to attack on it, and you are going to get the product over here like this. This is the product you are going to get here. Other thing remains as it is, so you write down this other part of this molecule as it is. Now here what is going to happen? Here you are going to get the compound like this, NO2 and this hydroxy group OH, right? And now this nitro group further treated with alkaline potassium permanganate KMnO4. This is again as an oxidizing reagent. What it will do? It will oxidize this will oxidize this nitro group into the carboxylic group, this, and so that you are going to get the product like this. Here you are going to get over here, I think CH2, and then this one C double bond OH, and this dash OH you can write. Another part of the organic compound, they are remains as it is. Here O, and it remains as it. Now this further treated with lithium aluminum hydride, or you can use as a sodium borohydride. They are the reducing reagent. What it will do? It will reduce the carbonyl group into the carboxylic, not this one. Here you remember, here is a carboxylic, C double bond O and OH over here. It get reduced into as a alcohol, so that you are going to get the product over here, O, this O, and now there you are going to get here O, this. There remains as it is. Now this hydroxy group also remains as it is, double bond, dotted line OH, and now this becomes as a OH. This is above the plane, right? And now next one, what you are going to use? You are going to use here the sodium hydride as a base here, NaH, sodium hydride. It will pick up the proton here from here, and negative charge form over there, and you are going to get the another product like this, O, this one, and now here again O, this as it is. Now here O minus, and here C double bond OH. That remains as it is, right? And after that you treat this compound with BnCl, benzyl chloride. what is going to happen? This is going to attack on benzyl group Cl, get removed, and you are going to get the product here. This one here, this group remains as it is, and this also remains as it is. They are as it is, right? Now here, what is happening here? OBN, and this one is a OH as it is. And after that, you treat this compound with the hydrolysis, selective protection here. Hydrolysis H3O plus, selective protection. Selective protection. After doing this treatment on this compound, what you are going to get? You are going to get the product over here like this. This one selectively, this group get open, and you are going to get the product here. This one HO, other thing remains as it is. Here OBN, and this hydroxy group as it is, and this protected group, it also remains as it is, right? And after that, it is further treated with the reagent like sodium periodate, sodium periodate, NaIO4. What it will do? It play the role similar to as a ozonolysis, as we know that ozonolysis means to break the carbon-carbon double bond, or it is playing a role just like as a lead tetraacetate for the cleavage of the diol over here. And after this one, what you are going to get? You are going to get the product is this type of the product. This protecting group, it remains as it is over here, and here you are going to get C double bond O and H. Here is the aldehyde. This group get, this diol get deprotected, and we are going to get here OBN, and this hydroxy group remains as it is. This is above the plane that is shown over there. Now again do the reduction here. You can use sodium borohydride, NaBH4. It is a reducing reagent. What it will do? It will reduce this aldehyde group into as alcohol, and you are going to get the product over here. This one. Now O, this they remains as it is. This group also as a remains as it is, OBN, and this OH. And here what you are going to get? Here you are going to get as a CH2OH, primary alcohol we are going to get. Then use as a what you are going to use over there. Now you protect this primary alcohol, and as we know that the reagent used for the protection of this one, what is the reagent generally used for the protection of this group? Let me clean the board first. Now this one further protected with which one? TSCl in presence of pyridine, right? Pyridine which will abstract the proton, which is basic in nature, which will abstract the proton from the negative charge that is going to attack over there like this TSCl, that is a tosyl chloride. At the beginning we already explained this type of the mechanism. Now let us see here what you are going to get. You are going to get other thing as it is, this hydroxy group also as it is, and this is also OBN as it is. And here what you are going to get? Here you are going to OTS, tosyl group, right? And now this group further treated with this one, that is a dimethoxy OMe, this type of the reagent used over there. And what you are going to get? This OMe, methoxy group is going to attack over there, and this type of the this group get open, and you are going to get formation of the product like this. Here OMe, and this side is OTS, and here they are remains as is OBN. This one is a hydroxy group. Now here what is going to happen? This is going to form as a automatically this get protected. 1-2 protection, this type of the compound is used for this protection, and after that you can treat this compound with tertiary butoxide. Tertiary butoxide, this is a strong base. What it will do? It will abstract the acidic proton from here like this. Acidic proton not from there. The highly acidic proton is this one. This will proton and then form as a double bond. OTS is a good leaving group, so that you are going to get the product. This one double bond we brought over here, and here is a OBN, and then dash 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 O dash 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 O, and this is a protected and OMe as it is, right? And after that the H plus acidic condition. Now here just treat with H plus. This is acidic condition. What you are going to get after doing this one? What you are going to get? There is a this type of the thing is going to happen over there. You are going to get over here the compound you are going to get here. C double bond O, methyl group over here. This one, then this double bond O, H, aldehyde group, and then this OBN remains as it is, then O dash dash O, and this group also remains protected, and now is a base is used over there. Here base is used which will abstract the proton, negative charge, and that is going to attack over there, and you are going to get the next product. There is a intramolecular aldol condensation. Intramolecular aldol condensation, and what you are going to get? You are going to get this type of the compound over there. C double bond O, then OBN, OH, not OH, I think, OBN, yes, this still remains over there, this one, and this one further treated with H2SO4, H2SO4, acetic anhydride and acetic acid deprotection can be done over there, and you are going to get the final product is this one, C double bond O, this one OH, this one is a OH, and this is our final product. Yes, this is our still here is a this can deprotect this one, still BN, OBN. Now OBN hydrogenalysis is avoided over there. Instead, this step is a very, very important and the essential one, because this OBN is not deprotected by this one, but only selectively this group get deprotected, 1,2 diol deprotected, that regenerated, and where we are getting as alpha beta unsaturated. Now we have to remove this one, deprotect, by using as a lipase deacylation. This is called as a lipase, that is the enzyme catalytic reaction, lipase. This is enzyme used, naturally enzyme used over there, and that is a deacetylation reaction takes place, and we are going to get our final product, which is a minus Pentanomycin like this. This is a OH, then OH, here is a OH. So this is our target molecule. I think with this we have completed as a 5 target molecule, their retrosynthetic strategy as well as how they are synthesized in the laboratory that we have seen, and what are the collective reagent used over there. Here is a methyl nitromethane is used for this conversion, then alkaline potassium permanganate, then sodium borohydride, then BnBr, NaH, DMF is used as a solvent, then hydrolysis, and after that we use as a sodium periodate, then sodium borohydride. Sodium periodate is used for the cleavage of 1,2-diol, and we are getting as a aldehyde, and then TSCl in presence of pyridine. It is always used for the protection of the primary alcohol, and after that we use as a methanol Me2 COMe2H plus, that selectively one get deprotected and another 1,2-diol protection, that is a selective, then tertiary butoxide, then finally that is a lipase deacetation is carried out, and we got the final minus Pentanomycin. In this way we have completed as a 5. Only last one is remaining, that is a minus sicamic acid, that we will see in the next time. Let us stop today here. Thank you. Have a nice day.